All right, so section 7.3, page 509, continuing with solving systems of equations. And if you'll notice today, we've got systems of 3 equations with 3 unknowns. So we've got x, y, and z. We've added a 3rd dimension. So on 509, the first thing that they talk to us about is row echelon form and back substitution. And they tell me that if I happen to be solving a system that is in row echelon form, and they tell me that just means that it has kind of like a stair-step pattern like we see here, and the leading coefficients are all 1. Now, when we get to chapter 8, we'll be talking a lot more about matrices and row echelon form and that type of thing. But for right now, if it has that stair-step pattern, like you see here, it's kind of like you've got 3 unknowns, and then you've got 2, and then you've got 1. So that little stair-step pattern, and the leading coefficients are each 1, then we can say that it's in row echelon form. The nice thing about that is that you can solve that system simply by back substituting. What they mean by that is that if you already know that z is equal to 2, couldn't you plug that into this equation and then find y? And then once you knew y and z, couldn't you plug those into this top equation and just find x? So that's what we want to do. So let's start with, if z is equal to 2, let's take that equation that only has 2 unknowns in it, y plus 3z is equal to 5, and let's put 2 in the place of z. So if we put 2 in the place of z, we'll have y plus z equals 5, so what's y? -1, yes. Alright, so now I know z is 2 and y is -1. I could come back up to the top equation. X minus 2y plus 3z equals 9. And let's put in what we know. Let's put -1 in for y and +2 in for z. So that would give us -2 times -1 is +2, and 3 times 2 is 6. So we would have x plus 8 equals 9. So what's x? X is going to be +1, right? Now when I go to write my answer, just like typically we write our answers in ordered pair, when I have 2 numbers, we're going to write these answers as ordered triples because I have 3 numbers. So in an ordered triple, it still just goes in alphabetical order, x, y, z. So I could go through and say my solution is going to be 1, -1, +2. 1, -1, +2. Alright, what if it is not in row echelon form, or in a form where I have 1 unknown and 2 unknown and 3 unknown equations, so that I can just back substitute? What if I have 3 equations and all 3 of them have 3 unknowns in them? What am I supposed to do with that? Well, there are several ways that you can solve that. In our textbook, on page 510, they talk to us about Gaussian elimination. In order to solve by Gaussian elimination, you're going to need to do elementary row operations. They haven't taught us elementary row operations yet. In chapter 8, when we work with matrices and we work with rearranging our matrices and configuring them into row echelon form, we'll learn elementary row operations. At that point in chapter 8, I'll teach you Gaussian elimination. But right now, we don't have the tools that we need to do that. So I want to show you a different way, something other that's in your textbook. I want to show you a different way of solving this system of 3 equations with 3 unknowns. And this is actually the method that we learned last year in Algebra 2, so this should feel pretty familiar to you. All right? If you have 3 equations with 3 unknowns, just to make it easier for us to track them, I'm going to call them equations 1, 2, and 3, just so that you can see what I'm using, okay? So the first thing I want to do is I want to choose 2 of those equations. Doesn't matter if you pick 1 and 2, or 2 and 3, or 1 and 3. Pick 2 of those equations. So I started by choosing 1 and 2, all right? I'm going to solve them, or I'm going to eliminate one of my unknowns. So I can choose to get rid of x or y or z, whichever you prefer. So I started off here and said, hey, it looks like y would be pretty easy to get rid of. If I just multiplied this top equation by 3, then I'd have a +3y and a -3y. So that's what I did. I multiplied this top equation by 3 to create an equivalent system. And so when I combined, my y's did drop out, and that left me with 14x, no y's, negative 7z, and 42. And again, just so we can kind of keep track of that, I'm going to call that equation number 4. So we created equation number 4 by eliminating y. All right, now I'm going to go back and I'm going to pick a different pair. So if the first time I picked 1 and 2, for this different pair, I could pick 1 and 3, or I could pick 2 and 3. I just need a different pair. Here's the key. Star it, put circles around it, highlight it, something. You must eliminate the same variable. So because I eliminated y with the first pair, I have to eliminate y with this second pair. So I look at this second pair and I say, okay, if I want to get rid of y, I could just multiply one of these equations by a negative 1, and that would make my coefficients of y opposites of each other, and it would eliminate. So I'll go through and I'll multiply this equation by negative 1. So that'll give me negative x minus y minus z is equal to 3. So if I go through and combine, then 4x minus x is 3x, positive y and negative y will drop out. Negative 3z, negative 1z is negative 4z, 11 and 3 is 14. I'm going to call that equation number 5 again, just so we can track it. Look what we just created with equations 4 and 5. If you put equations 4 and 5 together, that's just a system of 2 equations with 2 unknowns, right? Now we're right back to section 7.2. I'm good from there. So forget about all of this for just a second. Ignore all of this up here at the top. Think of this as a brand new problem right here. If I had a system of 2 equations with 2 unknowns, and I'm solving, I'd probably want to solve by elimination. So I'd go through and I'd multiply, let's say I want to get rid of the z's here. I'm going to multiply the top equation by negative 4 to get a positive 28z. And I'm going to multiply the bottom equation by a positive 7 so that I get a negative 28z. So when I combine those, my z's drop out. And I'll have 56 minus 21 is negative 35. And I'll have 168 minus 98 is negative 70. Divide both sides by negative 35, and x is 2. And then just like we saw in section 7.2, once you know what x is, you could plug it back into either one of these equations, either 4 or 5, to find z. So I thought equation 5 looked a little bit simpler, so I'm going to plug into equation 5. So it was 3x, since we just found x was 2, I'll put 2 there, minus 4z equals 14. So subtract 6 from both sides and divide by negative 4, and I'll have z equals negative 2. Now that I know what 2 of my unknowns are, I can go back to any one of these 3 equations up here at the top, number 1, 2, or 3, whichever one looks simplest. I thought number 3 looked simplest. So we can go through, I know what x is, I'll plug that in. I know what z is, I'll plug that in, and that enables me to solve for y. So once I have my answer of y equals negative 3, then I can just come plug that in. X was 2, y was negative 3, z was negative 2, so there's our ordered triple. So let's go back through that one more time. When you have a system of 3 equations with 3 unknowns, you're going to choose 2 of the 3 equations and combine them, get rid of whatever variable you want to. Choose a different pair. So if you chose 1 and 2, you would choose 2 and 3 or 1 and 3. Okay, choose a different pair, but eliminate the same variable. That's the key. So when I combine those and eliminate that same variable, those 2 new equations that I just created will create a system of 2 equations with 2 unknowns. That I know how to solve. So I'll solve it just like I had been doing in section 7.2. I will have 2 answers then. I'll have 2 of my unknowns. Then I can come back up to the top and plug it into any one of the original 3 equations to find that 3rd unknown. And I can write my answer as an ordered triple. Alright, now sometimes they try to be nice to us, and it almost to me seems a little bit more confusing. Because this is such a long, detailed process, sometimes they'll try and give us a little bit of a shortcut with it. So here's an example of that. In example number 2, we have 2 equations that have 3 unknowns in them, but then we have 1 equation that only has 2 unknowns in it. So they leave off one of the unknowns. Here's what I can do. When I go through and I combine these other 2 equations, like equations 1 and 2, if I'll notice that y is what got eliminated in that 3rd equation, if I'll combine 1 and 2 and eliminate that same variable, that will create my system of two equations with two unknowns, right? Because this is an equation that only has x and z in it. So if I'll create an equation that only has x and z in it, then this can become my equation number 5 and my equation number 4, that then I have a system of two equations with two unknowns, and I get to eliminate this whole step right here. So they're trying to be nice to us and ease us into it on some of the problems, but I just didn't want that to confuse you. They also show me in examples 3 and 4 that you can still get no solution and infinitely many solutions. Where that would show up is probably in this step right here. Once we got down to here, instead of getting x equals something, if our variables drop out and we get an answer like 0 equals -2, just like we saw in 7.1 and 7.2, that does still mean there's no solution. Or if in example number 4, everything drops out and I get an identity like 0 equals 0 or x equals x or 2 equals 2, then that means there are infinitely many solutions. So it will still look exactly like it did in 7.1 and 7.2, and it is still a possibility here. Now, they give me a couple of bold print terms on the bottom of page 511. They talk to us about consistent and inconsistent, which we've already learned. We learned that a system was inconsistent if it had no solution, and if it was consistent if it had exactly one or infinitely many solutions. Now we want to be a little more precise with our consistent systems. They tell me on the bottom of 511 that a system will be consistent independent if it has exactly one solution. It'll be consistent dependent if it has infinitely many solutions. And again, all of that is in italics and bold print on the bottom of 511. All right, so a couple of pages over, on page 514, they give me a graphical interpretation of three variable systems. Okay, I understand this process that we just went through. I remember that from doing it in previous years. I have no idea what I'm doing, though. I mean, what am I actually finding? What is this? Well, it might help us if we could picture it, if we had a visual representation of it. And so that's what they give us over on page 514, the graphical interpretation of a three-variable system. When you graph in 3 dimensions, you are graphing a plane. I mean, think about it. In 2 dimensions, it's a line, right? So if you take a line and you give it a 3rd dimension, then that would create a plane, kind of like a piece of paper, only it's going to extend infinitely in all directions. Okay? So if I have 3 of those equations with 3 unknowns, that means I have 3 planes. And so when I'm solving a system of 3 equations with 3 unknowns, I'm trying to figure out where 3 planes intersect. And so here are some examples of the answers that we're getting. Right? When we solved that problem a moment ago and we actually got an ordered triple, we got x equals something, y equals something, z equals something, that would look like this, where I've got a red plane, a blue plane, and a yellow plane, and they're all intersecting in that one little point right there. That's the only place that all 3 of them touch. Right? I also could get no solution. Now, when we had no solution with lines, they were parallel lines, right? So the first thing we might think of would be parallel planes. All 3 of my planes are parallel to each other, so they never touch. And that is absolutely one way I can get no solution. But another way I can get no solution is if for my 3 planes, maybe the yellow one intersects the blue one, and the yellow one intersects the red one, and the blue one intersects the red one, but all 3 of them don't touch anywhere. That's another way that I can get no solution. And that's important because I might find an ordered triple that works in 2 of my equations, but it doesn't work in the other one. And so, you know, like let's say you're in a multiple choice setting and you're taking that ordered triple and plugging it back in. If it works in 2 of the equations, that doesn't guarantee that it would work in the 3rd one. All right, then what does infinitely many solutions look like? Well, it could look like either of these. When we were working with lines, infinitely many solutions was overlapping lines. So the first thing we would probably think of is overlapping planes. So yes, if all 3 planes are overlapping, forming just one plane, that would be infinitely many solutions. But there's another way as well. If my planes all intersected and the intersection made a line, that's going to be infinitely many intersections as well, because there's an intersection there and there and there and there and there and there, and that line is going to extend infinitely in both directions. So that's another way that we can get infinitely many solutions. On 514, they also ask me to graph an equation in 3 variables. So we know how to graph in 2 dimensions, but how do we graph in 3 dimensions? All right. In the 3rd dimension, I'm going to add a z component. And the best way for me to envision 3 dimensions is to whatever room I'm in, if I'm in the classroom or if I'm at home doing homework in the kitchen or my bedroom, if I look in the corner of the room, the corner is a really good representation of 3 dimensions. Because I've got 1 dimension going up and down, I've got 1 dimension going left and right, and then I've got another dimension going forward and backward. All right? And so the way that we would represent that in drawing it out, it's kind of hard to draw 3 dimensions on a 2-dimensional piece of paper. But if I'm drawing that out, I could go through, x is going to go forward and backward, z is going to go up and down, and y is going to go left and right. Now, I know that seems bizarre because x normally goes left to right and y normally goes up and down. How come they did that? All right, it's kind of like we had our normal xy plane, okay? So x is going horizontal, y is going vertical. And you could not see that 3rd dimension of z sticking out the back of that. And so basically they took the normal xy plane and they just flopped it over so that then you could see that 3rd dimension sticking out the back. And so that's why it looks like x and y are kind of in a V shape on the ground and z is standing straight up, all right? So when I draw this, let's start with x. X is going to go forward and backward. The positive is going to go forward. The negative is going to go backward. Y is going to go left to right. Positive is going to go right. Negative is going to go left. And z is going to go up and down. Positive is going to be up and negative is going to be down. Now, that just looks like a great big mess. And so to clean it up a little bit, we typically just graph the positive axes and then add the negative ones when and if we need them. Okay? So let's see how we could graph 3x plus 2y minus 4z is equal to 12. If I'm graphing in 2 dimensions, okay, like I'm just graphing a normal line, 3x plus 2y, easiest way to do that is find x and y intercepts, right? So let's do the same thing in 3 dimensions. Let's find our x-intercept, our y-intercept, and our z-intercept. When I'm working in 2 dimensions and I'm finding the x-intercept, I put 0 in for my other unknown, right? So, like if I'm trying to find the x-intercept, then I put 0 in for y and I solve for x. We're going to do the same thing here. If I'm trying to find my x-intercept, I'm going to put 0 in for the other unknown. So I'm going to put 0 in for y and z and solve for x. If I'm trying to find the y-intercept, I'm going to put 0 in for x and z and try and find y. If I'm looking for the z-intercept, I'll put 0 in for x and y and I'll solve for z. Okay? So let's start with that first one, the x-intercept. If I put 0 in for y, 2 times 0 would be 0, so that whole piece goes away, right? If I put 0 in for z, negative 4 times 0 is 0, so that whole piece goes away. So literally it's like you can put one finger over the 2y and one finger over the negative 4z, because when you put zeros in for those variables, that whole piece of the equation goes away. And all you're left with is 3x equals 12. So what's x? 4. Same idea with the y-intercept. You could put a finger over the 3x because you're putting a 0 in for that x, and you could put a finger over the negative 4z because you're putting a 0 in for that z. That would leave you with 2y equals 12. So what's y? 6. And z-intercept, put fingers on 3x and 2y. So if negative 4z equals 12, what's z? Negative 3. So there are my 3 intercepts. So to plot them, I'm going to come over to my axes. It was a positive 4 on x, so positive comes forward. So I'm going to come forward 4 and put a dot. Y was positive 6. Positive goes to the right, so I'm going to go over 6 units to the right and put a dot. And z was negative 3, so I am going to need to draw in the negative axis for z. So I'll draw the negative axis going down and go down to negative 3 and put my dot. So there are my 3 intercepts. All right, so the book tells me that by plotting these 3 points and then connecting them with line segments, you can shade the resulting triangular region, and that way you've sketched a portion of the graph. Basically, what you're looking at is kind of like if the plane crossed over those axes, that would kind of be like the cross section that it would cut. So that's, of course, not the whole plane, but we can see a portion of it in that way. So that's how they're going to have us graph those equations with 3 unknowns. All right, so here is our homework for tonight on pages 519 and 20. Pages 519 and 20.